Kirchhoff 1824 to 1886, a distinguished German physicist, first clearly pointed out that the aim of the physicist is to describe the motions of bodies completely and in the simplest possible manner. But since a body is a limited portion of matter, which we may consider as made up of a number of small particles, it will be simpler to consider first the motion of a particle and then pass to the consideration of bodies in motion. However, since motion is merely change of position, it will be convenient first to learn how the position of a particle is defined. The word particle is used always to denote a body so small that its dimensions may be neglected in comparison with other distances involved. Thus, a baseball may be considered a particle when one is thinking only of its path through the air. But in the pitcher's hands, it becomes a body of very appreciable size, a body which he sets into rotation about a definite axis in order to give it any desired curve. Position of a particle in a plane. 2. When geographers describe the position of a town, they assume that the reader already knows the position of some point on the Earth, which may be called a point of reference. Such a point of reference for the surface of the Earth is the intersection of the meridian through Greenwich with the equator. This fixed, the location of a town is definitely described when two things are known about it, namely its latitude and its longitude. Thus, the island of St. Helena is in 15 degrees 55 minutes south latitude and 5 degrees 43 minutes west longitude. A similar method is frequently used in physics. For example, the position of a point, labeled as P, with reference to another point O in the same plane, is described when two mutually rectangular straight lines are drawn through the point O, and the perpendicular distances of the point P from these two lines respectively are given. The point of reference O is generally called the origin. The horizontal line of reference, labeled as OX, is generally called the axis of X, and the vertical line of reference, labeled as OY, the axis of Y. The longitude X of the point P is called its abscissa, while the latitude Y is known as its ordinate. Abscissas are positive when drawn to the right from the axis of Y, and negative when drawn to the left. Ordinates are positive when drawn upward from the axis of X, and negative when drawn downward. These quantities X and Y are known as the rectangular coordinates of the point P. They are a special kind of Cartesian coordinates, so called after Descartes, who first employed an algebra of this kind. In the laboratory, we have frequent occasions to draw curves, and this is generally done by locating points on coordinate paper in the manner just described. Navigators and surveyors generally employ a different method of locating one point with reference to another in the same plane. They give the straight line distance from the first point to the second, then they give the direction of the line joining the points. This method also is frequently used in physics and is known as the method of polar coordinates. The idea will be clear from Figure 2, where O is the point of reference and OX any known direction. There is no doubt about the exact position of a particle at P as soon as we know the distance r between the points O and P, and the angle theta, written as theta between the lines OP and X. The angular distance theta is always considered positive when measured in a direction contrary to that in which the hands of a clock move, a direction which is called counterclockwise. In like manner, theta is considered negative when measured in a clockwise sense. The line OX may be called the line of reference. Position of a particle in space. 3. If a point on the Earth's surface is to be described still more completely, we may choose the sea level as a plane of reference and give the altitude of the point. So, in mathematics and physics, one frequently describes a point by locating it first in a certain plane, as described in the preceding sections, and then stating the position of this plane with respect to some other plane of reference. It will be observed that, in general, 3 specifications are needed to completely describe the position of one point with reference to another, and when the numerical values of these 3 coordinates are once known, the position of the point is given without ambiguity. Thus, if the rectangular coordinates of a particle in space have the values x equals -4, y equals +6, z equals +3, one can proceed to locate it as indicated in Figure 3. Position vectors. 4. But a third and simpler way to think of the position of a point is to consider it as completely specified by a single straight line running from the point of reference to the point under consideration. If in figure 4 we know not only the length, but also the direction and sense of the straight line OP, we know all that can possibly be known about the position of the particle at point P. To any quantity such as OP possessing direction, sense, and amount, the name vector has been given. This class of quantities includes many of the most important studied in physics. A vector quantity is simply one which resembles a limited straight line in three particulars, namely, in the possession of direction, sense, and numerical magnitude. A vector which locates one point with reference to another, as in figure 4, is called a position vector, and is a type of vector quantities in general, of which we shall meet many examples in later pages. The usefulness of the vector in representing the position of a point lies in its clearness and simplicity. For purposes of numerical calculation, it has small value. Digression on scalar quantities. 5. The mere length of a straight line is the same in whatever direction the line may lie. The length of a straight line is, therefore, not a vector quantity. It is independent of direction. Quantities which do not have direction are called scalars. Philadelphia is a city 90 miles from New York. This distance is a scalar quantity. The information contained in this statement tells me only that Philadelphia lies somewhere on a circle of 90 miles radius described with New York as a center. But 90 miles southwest of New York gives me a vector quantity which locates the position of Philadelphia without ambiguity. A pound of sugar, 3 yards of calico, 2 gallons of water, a volume of anything, any amount of matter, are illustrations of scalars. Summary. 6. Summarizing, then, the position of a particle is nearly always described by one or the other of the three following methods. 1. Rectangular coordinates, in which the position of a point is defined by giving its distance from each of three mutually perpendicular planes. These distances are called the rectangular coordinates of the particle and are usually denoted by x, y, z. The three mutually perpendicular reference planes are indicated in figure 3 by YOZ, ZOX, and XOY. 2. Polar coordinates, in which the position of a particle is described by its distance r from the origin and by its latitude and longitude on a sphere whose center is at the origin and whose radius is the distance r just described. These three quantities are called the polar coordinates of the particle and are usually denoted by the letters r, theta, and phi, respectively. 3. Vectors, a graphical method in which the position of a particle is located as the terminal point of a single straight line drawn in a definite sense and in a definite direction from the origin. Position of a body. 7. Having thus far considered the position of a particle only, we now take up the position of a body which has already been defined as a limited portion of matter. For the present, let us deal only with perfectly rigid solids, that is, with bodies whose size and shape are each constant. If we consider a body merely as a system of rigidly connected particles, it is evident that its position is completely defined only when the position of each particle in the system is known. But since the body is rigid, this is equivalent to saying that its position is completely determined when we know the positions of any 3 points in the body, provided, of course, that these points do not lie in the same straight line. In other words, if a straight line and one point outside this line be located in a body, the position of the entire body is completely defined. It is clear, therefore, that a body may have many different positions in which 2 points in the body are fixed. For under this condition, it may be rotated through any angle about the straight line joining these 2 points. As we shall see later, it is often quite as necessary to consider the angular as well as the linear position of a body, while for a single particle, angular position is a term which has no meaning.